So our discussion today is going to focus on atomic structure. In particular, we are looking at atoms. Now, atoms, in their most basic description, their simplest understanding, they are the smallest particles of a given element. So if I have a sample of gold, the atom would be all the tiny particles of that gold that all share the same characteristics, have the same properties, have some sort of chemical identity in common. They may not all be identical in terms of what their numbers of protons or what their masses are. Not the protons, they're neutrons, or what their masses are. But they will at least have some things in common. They will all behave the same way in terms of their chemical reactivities. Now, the atom itself carries this description. It is a nucleus surrounded by a cloud of electrons. And if I were to draw that, I would start with my nucleus here in the middle. And that cloud of electrons would represent an area absolutely gigantic by comparison. So all the electrons exist in this cloud around the nucleus. The nucleus itself represents a very small part of the overall volume of that atom. So let's put this into perspective, because my drawing actually doesn't even do it justice. The electrons, which make up over 99.99% of the volume of the atom, they are negatively charged particles, and they are largely responsible for the chemical properties of the substance itself. So the electrons and how those electrons are arranged in space are largely responsible for whether the substance is air reactive or water reactive, or if it's inert, or if it has a high reactivity or a low reactivity. Those electrons effectively surround the nucleus. They are all around it, and they are moving in kind of a constant random motion. They are not moving in a circular kind of fashion like you've grown to believe based upon popular media. The nucleus, on the other hand, while the electrons make up 99.99% of the volume of the atom, they make up virtually none of the atom's mass. Electrons are incredibly tiny in terms of their mass. In fact, an electron is about 1/1820th of the mass of a proton or neutron. So in terms of mass, electrons are almost 2,000 times smaller in mass compared to protons and neutrons. So any mass information that we get about an atom comes from the nucleus itself. And inside the nucleus, there are two different subatomic particles. There is the proton. The proton has an atomic mass of about 1. and the protons are positively charged particles. The charge on the proton is equal but opposite of the charge of the electron. So in a neutral atom, every proton is matched by an even number of electrons. So if I have 30 protons, I'm going to have 30 electrons. Neutrons also have an atomic mass of 1. And they are neutral particles. They have no charge. So a neutron is technically slightly more massive than a proton is, but not enough to care about. They have effectively the same atomic mass, and that atomic mass, again, is almost 2,000 times greater than that of an electron. Neutrons, however, have no charge. They are neutral in their charge. So those are the 3 primary subatomic particles. Now, if you were taking an advanced physics class, you would learn that there are subatomic particles that make up these subatomic particles. We get into things like quarks and muons and bosons and other kinds of subatomic materials that have made their way into some of the storylines coming out of this major scientific community in the past couple of years. But we're really just going to focus on these 3 because these 3 really are kind of the important ones to look at when it comes to atomic and elemental characteristics and reactivity. Now, there are some key definitions that we do need to be aware of. First of all, the atomic number of any element is equal to the protons in the nucleus. If I'm looking at my periodic table, that atomic number is given to me as the number in the top of that box. So hydrogen number 1, helium number 2, lithium number 3, those are the atomic numbers of those elements. And that tells us the number of protons in that nucleus. We'll skip these next 2 for just a second and get the other number on the periodic table. That decimal number at the bottom, that is the atomic mass of the element. Now, the atomic mass of the element is an average mass. And what we mean by an average mass is that if I take a sample of atoms of that particular element, on average, they will weigh that much. Now, that's not to say that any one of them is going to weigh that exact amount. In fact, that's probably not going to be the case. But on average, if I have hundreds or thousands or millions or billions of atoms, which in the case of most samples that we would collect, the actual number is somewhere around anywhere between 10 to the 18th and 10 to the 25th atoms. So 10 to the 18th would be a million. 10 to the 25th would be 10 million billion. We're talking about large quantities of atoms. And so average mass works out just fine for us because it's going to be almost an impossibility to get an individual atom for our purposes. These 2 in the middle are not found in the periodic table. They are the mass number and the isotope. Now, remember when I said atoms were kind of the fundamental unit of an element, but they aren't always exactly the same? This is where we get into that. Isotopes exist for given elements. And what an isotope is basically we have the same chemical identity. The atomic number is exactly the same, but our number of neutrons is different. So take carbon, for example. Carbon primarily exists as carbon-12. Carbon-12 has 6 protons, 6 neutrons, and 6 electrons. However, there are 2 other forms of carbon. There's carbon-13, which has 6 protons, 7 neutrons, and 6 electrons. And there is carbon-14, which has 6 protons, 8 neutrons, and 6 electrons. The thing that differentiates those isotopes from each other is their mass number. And we identify them based upon their mass number.
Shit, I'll screw up Ryan and hate it. It's bro. It's bro. It's bro.
So isotopes are often identified by their mass number, meaning carbon-12, the 12 there is the mass number of the carbon, carbon-13, carbon-14, the 13 and the 14 are mass numbers also. So it is possible to have different atoms of the same element and have them be different from each other. Where they are going to be different is in their mass number, not in their atomic number. Again, atomic number helps to identify the element. If I go from 6 protons to 7, I go from an atom of carbon to an atom of nitrogen. Atomic number does not change for a given element, but a mass number can change. All right. Now, the reason I stress this so much is because mass number and atomic mass are probably 2 of the more confused concepts in this course. It'll inevitably come that on the exam 2, when we cover this concept, and I ask you to give me the mass number for a particular isotope of phosphorus or whatever, there will be at least one, probably 2 or 3 of you that will write down the atomic mass of phosphorus from the periodic table, as opposed to looking at how many protons and neutrons are in that particular isotope in the problem. There is a difference. Remember, the mass on the periodic table is an average. It does not represent any singular isotope. It represents accumulation of all of the isotopes together. Now, based upon the number on the periodic table, we can get a pretty good idea what the most common isotope of each element is. So, for example, if I look at carbon, the atomic mass of carbon is 12.01. I just told you that the 3 different isotopes of carbon are carbon-12, carbon-13, and carbon-14. So if the average mass is 12, and those are my 3 options, which isotope is the one that's the most common? the carbon-12. And if I look at chlorine, chlorine has two common isotopes, chlorine-35 and chlorine-37. Based upon the atomic mass of chlorine, which one is the more common? 35. You can very quickly get that kind of information by looking at the periodic table. Just because isotopes exist doesn't mean they all exist in the same proportion. So in the case of carbon, carbon-12 makes up over 99.8% of all of the carbon in our planet. Carbon-13 and carbon-14 make up the rest, and it's not very much. Let's look at some symbology here. Now, this is a nuclide notation that is often used to express different isotopes and kind of give you all of that information all in one spot. So this is sometimes referred to as nuclide notation. It is sometimes referred to as isotope notation. We also can refer to it sometimes as AZX notation. But the idea is this. I've got the mass number on top. That's my letter A. And again, mass number is protons and neutrons together. I've got my atomic number on the bottom. That's my Z. And I've got my elemental symbol X out in front. Now, the important thing to remember is that these two, Z and X, tell the same story. The atomic number dictates, identifies the element. So my atomic number is 12. My atomic symbol should match that, which means I look at the periodic table and element number 12 is magnesium. Mg would be my value of X. Now there is one other attribute here that is not mentioned that is worth looking into. I'll add it right here. Sometimes nuclide notation also includes another piece here on the top right corner. And that piece is called the charge. We can find the charge of any species by taking the number of protons, that is the atomic number, and subtracting from it the number of electrons. So when our atom is neutral, which is most of the time, there will be nothing in that spot. But in certain cases, we might have a -1 charge. -1 charge would mean we have one extra electron. So our atomic number would be whatever it is. The charge would, the number of electrons would be one more than that. Might also be the case where we have fewer electrons, positive charges. And so this formula gives us kind of the balance accordingly. All right, any questions about this notation? All right, so let's do a couple of practice problems here. None of these are charged species. So let's look at the number of protons and neutrons associated with each. Now, I do want to point out one other thing to you. I mentioned this in passing. This is another form of isotopic notation where we give the elemental symbol followed by the mass number: chlorine 35, carbon 11, gold 198. And they give us kind of the same information because, again, if I know the elemental symbol, I should already be able to figure out what the atomic number is, since it is on the periodic table with that symbol. So for chlorine 35, my atomic number is 17. My mass number is 35. Remember, atomic number is equal to the number of protons. So I have 17 protons. My mass number equals protons plus neutrons. So 35 is equal to 17 plus my neutrons. I would have 18 neutrons in total. $35 is equal to 17 plus n. So I subtract 17 from each side. N is equal to 18. For carbon 11, my atomic number is 6. So my number of protons is equal to 6. Neutrons is equal to the mass number 11 minus the atomic number 6. So there are 5 neutrons. For gold 198, the atomic number of gold is 79, so the protons would be 79. My neutrons would be 198 minus 79. Which would be 119. How many electrons are in each one of these? So how many electrons in chlorine 35? It would be 17. Now, if you're thinking 35, you're on the right track. You just picked the wrong number. If we have a neutral atom, which this one is, there's no charge on it, then the number of protons and the number of electrons is the same. So how many electrons in carbon 11? It would be 6. How many electrons in gold 198? 79. All right, any questions with any of these 3 examples? All right. Want you to take a minute, work this one out by yourself. try to determine what goes in each of the blank spots. Take a couple of minutes to try to figure that out. And we'll pick up in about 3 minutes. All right, let's see how we did. So for number 1, we are told that number 1 is lead, Pb, and that it has 126 neutrons. Now, from that information, we should be able to figure out the rest. Because with the symbol of Pb, we can find Pb on the periodic table and see that its atomic number is 82. And that also matches its number of protons. To find the mass number, I need to add together 82 plus 126. And when I do that, it gives me 208 as the mass number for lead. So we are dealing with lead 208. And so if I want to turn this into nuclide notation, I would have the lead. Now I would just put the symbol, the mass number there, and the atomic number there. In number 2, I'm given the atomic number and the mass number. Well, atomic number is 39, so that means that the number of protons is also 39. Mass number minus protons will give me the the neutrons, which would be 50. For the symbol, atomic number 39 corresponds to element Y, yttrium. And I would put the mass number on top, 89. The atomic number on the bottom, 39. And there we go. Last one, we are not given anything about the atomic number or the protons. We're just given a mass number and a number of neutrons. So we're kind of working backwards compared to the previous one. So mass number of 31 minus 16 neutrons would give me 15 protons. 15 protons means an atomic number of 15. Atomic number 15 takes us to phosphorus, P. And to finish out the symbology, 31 is its mass number, 15 is its atomic number. All right, any questions about these 3 examples? All right, then let's continue. I mentioned previously about the idea of ions. Ions exist when we have an imbalance of protons and electrons. And that imbalance of protons and electrons gives an ion its charge. As I mentioned previously, we can calculate the charge of an ion by taking the number of protons and subtracting from it the number of electrons. And by doing so, this number is either going to be positive or negative. If there are more protons, it's going to be positive. We're going to call that a cation. Cations are positively charged. In all, they have fewer electrons than the neutral atom. So somewhere along the line, the atom has given away electrons to create this positive charge. Anions, on the other hand, are negatively charged. They have more electrons than they do protons, which means that somewhere along the line, that atom has added electrons in some kind of way. But the important thing to notice here is always the electrons that are changing to give a charge. If the proton number changed, we'd be talking about a different element. Really important point to make there. It is always the electrons that are changing. Electrons are being added or electrons are being removed. That is how we get charge. It does not get charged by changing the number of protons. Because again, if we change the number of protons, we change the identity of the element. So we're going to close up today by looking at the same kind of problems that we just did, but now accounting for charges and charges being present. Here I have 5 charged particles: sodium plus, chloride ion, oxide ion, aluminum 3 plus, and phosphide ion. What we need to do is identify the number of protons and electrons in each. Now, the first part should be easy. How many protons in a sodium atom? 11. How many protons in a chlorine atom? 6. How many protons in an oxygen? 13. In aluminum? 13. In phosphorus, we just covered 15. So that part's easy. We already knew how to do that. We just need to find that element on the periodic table, write down its atomic number. What about electrons? How many electrons in sodium plus 1? This is where that equation comes in. Go ahead. It'd be 10. Remember, charge is equal to protons minus electrons. So if I have a plus 1 and 11 protons, algebra says I should be able to get 10 out of that. What about for chloride? Cl minus 1. How many electrons are we dealing with there?
16.
It is 18, Michael. That's right. So where does that come from? Again, the same kind of idea, the same kind of logic, the same kind of algebra. -1 is equal to 17 minus my number of electrons. If I add electrons to each side, and then add 1 to each side, I get 18. How many electrons in my oxide 2- ion? 10. I need to add 2 electrons to the number of protons. How many electrons in my aluminum 3 plus? 10 also. Since it's positive 3, I'm going to take 3 electrons away. 13 minus 3 is 10. How many electrons in my phosphide 3 minus ion? 18. I got 3 extra electrons. 15 plus 3 gives me 18. Now, what I want you to notice here, kind of our closing thought today, it's going to springboard us into Friday. The fact that these ions landed on common numbers of electrons is not coincidental. There's a very particular reason why it happened. And that'll be one of the things that we get into on Friday is why do atoms behave the way that they do? Why is it that ions tend to fall into categories that give them the same number of electrons as noble gases? Because element number 10, neon, that's a noble gas. Element number 18, argon, that's a noble gas. Why is that the case? Let's do one more example just as a closer here. What is the symbol for the ion that has these descriptions? 20 protons and 18 electrons. Element number 20 is calcium. If I have 20 protons and 18 electrons, how many, what's my charge? Yes. Positive what? Positive 2. Remember, protons minus electrons is equal to charge. So it's not enough just to say positive or negative. We have to assign a value to that positive or negative. -1, +3, -4, whatever the case is. For number 2, 16 protons and 18 electrons. 16 protons would give us sulfur, S. This would be a -2. 26 protons and 23 electrons. Element number 26, iron. 26 minus 23 is a +3. Another thing that we will often find, metals tend to make positive charges. Non-metals tend to make negative charges. Again, Friday, we're going to get into all of that kind of stuff as we start to describe physical and chemical properties inside of the periodic table, inside of those individual families. So that is all for today. Try to stay warm and safe. If you got to drive home today because you're commuting, be careful out there. I'll see you on Friday. Yes. The chapter 3 homework and the chapter